Hello, students. In this video, I'm going to go over how to solve question 15 from this last homework assignment. And in this question, what I was looking for is the following. So we have phosphate or phosphoric acid, which is this triprotic acid. You can see here it's H3PO4, and it can be deprotonated at 3 times because it has these 3 acidic protons, but each one of these has a different pKa. And those are shown here on the screen. And if we have a 0.1 molar acid or 100 millimolar acid, the question is how much of each of these possible compounds, so H3PO4, H2PO4 minus, HPO4 2 minus, or PO4 3 minus, how much of these are present at every single integer pH unit from 1 to 13. Before I go into how we do this, I want to talk a little bit about what we expect to see. So first, we have these 4 different components that are all related. They're all based on H3PO4. So if we add H3PO4 and all we're doing is changing the pH, we're just changing which one of these 4 phosphate-related compounds we have. And so that means that all 4 of our compounds here have to add up to the initial concentration of our phosphoric acid. And that makes sense because all we're doing is deprotonating our acids. So there's nothing we're doing to chemically react these acids, we're just deprotonating them. So if we start with 100 millimolar or 0.1 molar, the same thing, we can't change that. So we're essentially going to have a systems of equations where this is our main equation we're going to use to solve. Now, how do we figure out the relative ratio between these 4 compounds? And that is where the Henderson-Hasselbalch equation comes in. So the Henderson-Hasselbalch equation tells us the relative ratio of acids to conjugate bases in a buffer system at a certain pH. And so we're going to use that. Now, what do we expect? Again, remember from class, what we expect is that if we are near the pKa, we'll have an abundance of both acids and bases. So again, according to our Henderson-Hasselbalch equation, which are right here. So the Henderson-Hasselbalch equation is the pH is equal to the pKa plus the log base 10 of the concentration of conjugate base over the conjugate acid. So if this is my equation, if my concentration of base and acid are equal, the log of 1 is 0, and so my pH is equal to pKa. So for example, if I were to ask you what is the abundance of all of these different guys at the pH of 2.12, we would say, well, if at 2.12, the H3PO4 is exactly equal to the H2PO4. Now, what about the other guys? Well, if we rearrange this expression, we'll get the following. So I'm going to subtract the pKa over to the pH side, and then I'm going to raise this to the 10, which gets rid of the natural logarithm. So what I have here is that my concentration of conjugate base over my acid is equal to 10 raised to the pH minus the pKa. And this tells us our ratio. So if my pKa is much, much higher than my pH, so for example, in this first case, if my pH is 1 and my pKa is, say, 12.44, what that means is that this 10 raised to that number is going to be 10 to the minus 11. So I'm going to have minus, for every 1 HA I have, I'm going to have 10 to the minus 11 A minus. Or let's put that the other way around. For every 1 A minus I have, I'm going to have 10 to the 11th HA, which is basically none. So what we would expect is that when we're far away from the pKa's, we have almost none of the other acid compounds. So how do we actually do the math? How do we show this? And it's fairly straightforward. So what we're going to do is just apply this Henderson-Hasselbalch equation, and again, rearrange into this form. And we're going to apply that 3 times for each deprotonation event that we can have. So first, we'll start with our first deprotonation event. And so our conjugate base for that is H2PO4 minus. And then the acid for that is H3PO4. And that ratio then is going to be equal to 10 to the pH minus, and here I'll say pK1 instead of pKa to indicate the first deprotonation event. And so for us here, that is 1 minus the pK1 there, which is 2.12. So 1 minus 2.12 is minus 1.12. So 10 to the minus 1.12. And here, what this is going to tell us, if we can rearrange and get that H2PO4 minus is equal to 10 to the minus 1.12 times H3PO4. And this, now we can take this and plug this into the equation for what H2PO4 is. And this is going to tell us how much of our acid has been deprotonated, because we know that so 10 to the minus 1.12 is approximately 10 to the minus 1, which is approximately 0.1. So it's going to be about 1/10. So we're going to have about 1/10 of our acid, of our original H3PO4 is going to be in this H2PO4 form. But what about the other two? Well, for the other two, we do the exact same thing. So we go ahead and construct another Henderson-Hasselbalch equation here using the second deprotonation event. So HPO4 2 minus over H2PO4 minus equals now 10 to the pH minus, here it's pK2. And so for this, right, the pK2 is 7.21. So here this is 10 to the minus 6.21. And then we can again rearrange and get HPO4 2 minus is equal to 10 to the minus 6.21 H2PO4 minus. Now what's H2PO4 minus? Well, heck, we have an expression for it right here. So we go ahead and plug that in. And that's going to give us 10. And the way that exponents work, of course, if you multiply the exponents, you add them. So it's going to be 10 to the minus 7.33 times H3PO4. And now we have an expression for HPO4 in terms of H3PO4. And we can plug this into our equation here for HPO4. And we can do the same thing for PO4 3 minus. I'm not going to go through the steps. It's the exact same. Essentially, what we get is that our PO4 3 minus is equal to 10 to the minus 1.12 times 10 to the minus 6.21 times 10 to the minus now 11.44 coming from our pK3 there of 12.44 times the concentration of H3PO4. So it's the exact same steps I did before, and then we again just plug in. So now we have this expression here that's going to relate how H3PO4 is, or how HPO4 is related to H3PO4, and we can substitute that into our third Henderson-Hasselbalch equation, which I'll go ahead and write. So PO4 3 minus over HPO4 2 minus is equal to 10 to the pH minus pK3 equals 10 to the minus 11.44. All right, and so we can substitute these all in and we get the following. So I'm going to pull out H3PO4 because that's going to appear in every term. And then what do I multiply that by? Well, I have my initial 1 from up here. And then for my second term there, I have plus 10 to the minus 1.12. And then for my third term, I'm going to have 10 to the minus 7.33. And my fourth term, I'm going to have 10 to the minus 18.77 from adding 7.73 or 7.33 plus 11.44. And that is all equal to the 0.1 molar that I know all my different components have to add up to. So from here, we can simply add these together and solve. Now, I'm going to go through what this is, and you might be able to realize that two of these numbers are essentially 0. So 10 to the minus 7 and 10 to the minus 18, when added to a number like 1, is essentially they're not going to make a difference to that number. So we really only need to consider these first two numbers here. And so what that gives us, if we add just these first two numbers, is that 1.076 times H3PO4 is equal to 0.1 molar. So we can divide 0.1 by 1.076, and that gives us 0.0929, and I'm going to write that in terms of millimolar because I like whole numbers better than fractions. This gives us H3PO4 is equal to 0.0929 molar, or 92.9 millimolar. And this makes sense. So if we go back and look at our original equation, we are at pH 1. We are approximately 1 pH unit away from the pKa. So we would expect for that deprotonation event there to be about a 9 or 10 to 1 of our acid to our base. And so we see approximately 90 millimolar of our acid. Now we can figure out what our H2PO4 is just by taking the concentration of H3PO4 and multiplying it by 10 to the minus 1.21, just like we have right here. So we do that, and we end up with 7.0 millimolar. And here you can see with, of course, rounding that comes in, this is essentially all of our acid. So here we're at 99.9 millimolar, which is basically everything. We can do the same thing for our others. So again, just plugging in this concentration of H3PO4 into our various other equations here will tell us how many of the other molecules are present. But as we expect, based on the Henderson-Hasselbalch equation, they are vanishingly small. So what we get for our HPO4 is we would get 4.3 nanomolar, which is 1,000 times, a million times less than the others. And then it's even smaller for PO43 minus. So if we do a PO43 minus, we would get 15.8. I think that's zeta moles, or zepto. I think zeta is big. Zepto moles, so almost none. This is 10 to the minus 21, so 15 times 10 to the minus 21 molar. And so both of these two here, it's fair to say that these are approximately 0 because they're so much smaller than the rest of them. And that is what we expect based on the Henderson-Hasselbalch equation. Now, to do this for all the other pHs, it's very straightforward. All I need to do is change the pH. So I had this pH that went into every single equation, and all I need to do is to change that number. And I'm not going to go through the math in too much detail, but what we would get when we do that is the same thing at the end of the day. We would have H3PO4 again as our base, and then we multiply that by the same thing. So we have 1, but now instead of having 10 to the minus 1.12, instead of having 1 minus 2.12, we have 2 at our new pH. 2 minus 2.12 is 10 to the minus 0.12. And then we just keep building off from there. So then instead of multiplying those first two, we would multiply again just with 2's there instead of 1. So we would get 10 to the minus 5.33, and then plus 10 to the minus 15.77 here. I'm trying to do math in real time in my head. And this is equal to 0.1. And again, we go through and solve. Again, we notice that these numbers are very small compared to our first numbers. So what we end up getting is 1.759 times H3PO4 is equal to 0.1. And again, now we can solve for this. And this gives us different concentrations. So this gives us, let me just copy these. So it gives us H3PO4 here equal to 56.9 millimolar, and then an H2PO4 of 43.1 millimolar. So here we can see as we go from 1 to 2, we are getting closer to the pKa. We are almost at that pKa. And if we were at the pKa there, the pK1, we would see 50-50. Since we're not quite there, we don't quite see 50-50, but we're pretty close, and we see 57 to 43 3 as we near the pKa. And again, for our HPO4 2 minus and our PO4 3 minus, we see very small numbers. So this is 266 nanomolar and 9.7 attomolar. Again, these guys are approximately 0 because they're much, much smaller than our others. So this is how we solve the problem. We get answers that make sense, but it's kind of a pain, and I wouldn't expect you to do these calculations 14 times or 13 times, however many times it is. And that's why we turn to Excel. So for the next part of this video, I'm going to go over how we use Excel to solve this problem. All right, so here we are in Excel. I have the following Excel set up. I have my columns here. It's going to tell me the concentration of each of my acids here. And then I have their pKa's over here. And what we can do in Excel is very easily do the same calculations over and over again, changing some of the numbers slightly. So for example, we want to do it at all these different pHs. We can go ahead and put a 1 in here. And then we can drag this down. Now, it usually doesn't automatically change. So after we drag it, we have all these 1s. We don't want these. You can click on these autofill options and say fill series, and that will increase by 1 every time. So this will give us our 1 through 13, just like we want. And now what we need to do is go ahead and type our equation into this column. So to do that, if you want to type an equation into Excel, you need to start with an equals sign. So you start with this equals, and we want to say, okay, well, what is our concentration of H3PO4? Now, remember what this was. It was this whole complicated slew of these things where we had 1 plus 10 raised to the minus pKa, and then we went on and on from there, or the pH minus pKa. So what we can actually do is to simplify this for us a little bit is we can come here and make a new column. You'll just have pH minus pKa. And we can do that in this column. So then we'll say this is equal to the pH minus the pKa. And here that's going to give us this 1.12 that we're going to want to use to substitute into all of these equations. Now, we can make this easy for ourselves. So what we ultimately want to do is probably drag this down. We want to drag it down and make it just the same at every single spot. But as you see, this is giving me some funny answers. Now, why is it doing that? Because in Excel, when you drag it down, so again, I just clicked right here on this little box to drag it down. What it's doing is dragging all of the numbers down and changing them as well. And we don't actually want that. So here we want to take this number, A2, and subtract H1. And we want to do that at 3. So for this box here, we want A3 minus H1. We drag this down. But what it's doing is A3 minus H2. So to get that to change, we just got to come up in here to our H1 and put a $sign. And now it won't change at the 1. So now if we drag this down, what we will expect to see is just our subtraction. So here we have minus 1.1, minus 1.12, and then we have all of our good numbers here. And we can also drag this over and get the same thing, although that, so what it's doing is, as I dragged it over, that's wrong again, is that it also moved A. So we don't want it to move A, so we can go in here and say, don't change A. So we put that $sign in front of the A. And now when we drag it over, it will change appropriately. So here we have all of our pHs minus our pKa. So again, the concentration of H3PO4, right? We just solve for this. This was equal to 0.1. Again, this is going back to the math we just did. It was equal to 0.1 divided by the following. It was divided by 1 for the 1 H3PO4, and then plus 10 raised. So when we want to do an exponent, you do that caret. So 10 to raise to the this number here, so the pH minus pKa, so the minus 1.21. And then to that, we added 10 to the, and then we had to add these two numbers, and you have to add the exponents work. So this plus this plus 10 raised to the sum of these again. So this plus this plus this. Now, remember, as we went through the assignment, I ignored these last two. In Excel, we don't want to ignore these last two because as we get to higher pHs, they will become the more dominant force here. And what I'm actually going to do is instead of having it in molar, again, I want it in millimolar. So instead of doing 0.1, I'm going to do 100 divided by that because we have 100 millimolar. Okay, I have some sort of error. I missed a parenthesis. I'll accept the error. And here I get 92.9, which is exactly what we got before. So again, I want to drag this to all my columns, but I had to be a little bit careful as I drag this to all my columns and rows because it's going to do the weird things that we saw with the pH minus the pKa over here. So I'm going to go into this equation and say, okay, what do I actually want to do? And I don't want the columns of these guys changing. So if I don't want their columns changing, but I do want their numbers changing as I drag down, I'm going to go ahead and put in a dollar sign here at all of the letters. So when I put a dollar sign into all of the letters, that's going to keep the letters from changing while allowing the numbers to change. So the columns aren't going to change, but the rows will change when I drag down. So hopefully this will work and we can drag it across and see what we get. And it didn't work. Why didn't it work? Oh, because that's not what we're doing at all here. So that should work as I drag this down. Now, if I drag it down here, this should work. Yeah, so here as I drag this down, we now get to 56, and then we can keep dragging it down and we should see the proper other numbers. We'll get that there. So we don't drag this across. What we have to do, right, is we have to say, well, how do we get there? So how do we get from this 93.9 or 92.9 to our concentration of H2PO4? Well, we multiplied it by 10 to this. So this number here, so the concentration of H2PO4 is equal to 10 to the minus 1.12 times this concentration. So we do that, and there we get our 7.0, and we drag this down, we should get 43, yep, so that's all working. And then we can do the same thing over here. So this number was equal to 10 raised to the sum of these two numbers, so this plus this, then multiplied by our 93, or 92.9 here. Again, very small, and this number was equal to 10 raised to the this plus this plus this. All of this, guys, multiplied by 92.9. All right, I'm missing an Excel errors at time. I'm missing parentheses. There we go. And so we can see 92.9, 7.0, and then two very small numbers. Now, what I can do to make this a little easier for myself is I can go in here to format cells. And I can say that I actually don't really care about all of these digits. What I really just want is maybe two significant figures after there. So I want to look at it like this. And that, again, is just going to simplify my numbers. And we can see that these guys are so small, they're essentially 0. And I can, of course, drag them down. And hopefully I should get answers that make sense. So now, as I drag this down, what do I expect to see? Well, this is going down. And at some point, this should become essentially 0. And that should happen roughly 2 or so pH units above the pKa. So after about pH 4, we really shouldn't expect to see too much H3PO4 anymore. So let's go ahead and see if that works out. And that does. So we see very small amounts again after 4, but they're essentially gone. And what we see as we drag these is it should go up and then down. And then these ones should, again, this one should also go up and then down, but more centered around that pK2 of about 11. And this one should be dominating as well towards the end. So what we see here is these answers actually make sense. So we start high, we lose our first acid, we then get a bunch of our second acid. That goes down, and we gain some of our third acid, and then that goes down, and then if we finally gain our fourth acid at the highest pHs. And if we kept going, so why not? Let's go ahead and add a 14 in here. So very basic pHs. We see almost all exclusively in this PO4 3- form. And so that is how you go about solving this problem. I think this problem was a little bit challenging, and there's probably also some Excel issues. I know students aren't always super confident in working in Microsoft Excel, but you can see why we would want to do that. That we only have to do the calculation really once, and then it'll do it for us, however many more times we want. And we could even imagine going to higher pHs if we were crazy, but we're not going to do that. So there you go. That's how you solve this problem. I hope you find this helpful, and also helpful to work through these problems, and also helpful in understanding what's going on when the pH changes with different acids.